Our next presentation starts off with depicting a rather desperate future. It's a future where there's no more Portland cement, which is going to send shivers down everyone's spines. But what could be done about it? Mark Connelly from Atkins and Philippa Horton from the University of Cambridge is going to explain to us how the world might not be so dark after all. Thank you.
Good afternoon. So, thanks for the kind introductions. Happy to be here, join you all this afternoon. Joined by Philippa Horton from Cambridge University, who will do a bit of a double act on the presentation today. So, just in recognition of the fact that it is the first presentation after lunch, we've tried to limit the amount of words in the presentation, so it's mostly pictures you'll be glad to hear. So Philippa and I represent 2 of the 8 partners on this Innovate UK project. The other partners that we've got are the Materials Processing Institute with their steel and metals research background. We've got Celsa Group, who produce steel on an industrial scale. Cambridge Electric Cement, that are a spin-off company from the University of Cambridge, who are responsible for the invention and the development of electric cement and the cement to zero process. Balfour Beatty and Atkins Realis, who look at the engineering, the design, the planning, construction side of things. Day Group, who are involved in concrete and demolition waste and recycling. And lastly, Tarmac, who are cement and aggregate specialists. So, where do we want to start? So, trying to keep this a bit light-hearted, again, to recognise the fact that first presentation after lunch. So, I recently went to see Back to the Future, the musical, in London a couple of months ago in August. And excellent show, by the way. If you get a chance to go and see it, I would recommend it thoroughly. But it did get me thinking, you know, and I'm assuming that most of you have probably seen the movie or the movies, but it did get me thinking about what they might say if they were able to go forward to 2050 and come back and tell us what the future of construction and cement production and concrete production might look like. I think Doc Brown's unlikely to say that we don't need roads, which is one of his famous quotes. I think we will. I think we're quite a few decades away from not needing roads. But what might he say, if he was to say anything at all, about infrastructure, how we design things, how we manufacture and construct? So I'm hoping that he might say that we don't do things the same in 2050 like we do now, that there's been a bit of a step change in terms of the materials that we use and the process that we use, and we're a bit more sustainable. We need to be a lot more sustainable. So picking up from all the good presentations this morning, if we can get all of that good thinking together, then hopefully it'll be a much brighter future in terms of that. So, what do we mean when we look at the future? I always like to, in trade industry, press, magazines and things, I always show these kind of, you know, really futuristic representations about what the roads of the future, what the streets of the future are going to look like. And it's all about, you know, automated cars and everything being connected and that kind of thing. What we don't focus on so much is actually how we're going to build it, how much it's going to cost, where's the materials going to come from, how we're going to do it sustainably. We're starting to talk about that and have those conversations, which is great. But we do really have a big challenge ahead. So if you think about 2050, which is, I know, I think Paul, you mentioned 2045 earlier as Skanska's target, but generally if you think about 2050, it's just over 26 years away. 26 years isn't a long time, it's a generation. If you look back 26 years ago from now, 1997. Quite a relatable year, actually. I think it was Rachel that talked about the Kyoto Protocol. That was 1997. We had the first computer beating Gary Kasparov at chess. We had the first Harry Potter book. We had Dolly the sheep. Quite a pivotal year, actually, when you come to think of it. But you know, it's not that far away, so we've got a lot of work to do. There was a UN Environment Programme guidance report issued recently, talking about building materials and how they're set to dominate carbon emissions. Cement and concrete being one of the big three, along with steel and aluminium. But we're here today to talk about concrete, obviously, and cement. And concrete products at the moment currently use round about or less than 1% recycled materials. So how could we improve that going forward? So I like to look back a bit. Pippa's desperate to go. And think about what we do already, what we've done. So I was looking through some of Atkins' case studies recently, and I couldn't really find much on recycled concrete. Probably reflects the fact that we don't use it much. But I was involved in this project. I was the Atkins project manager on a project 15 years ago, just outside Glasgow, M74, where at the time it won a Sequal Excellent Award. At the time, it was quite sustainable. There were two, I think it was, high-rise buildings, high-rise flats that were demolished adjacent to the scheme, but as part of the scheme development. And there was about 400,000 cubic metres of demolition waste reused in the project, so as crushed, effectively, embankment fill, which, good news story, but was it really valuing the material in a way that got best value from it? So there's that project. There's also Network Rail have got a recycling and reuse facility down in Whitemoor in Cambridgeshire. They've had that for about 10 years or so. But again, a lot of the demolition waste gets reused, but maybe not in recognising the value that it has. So what solutions are there for cement and concrete? I'm going to hand over to Pippa now, who's going to help define what the problem is.
The clicker. Thanks. Sorry. Really nice to be here. I'm from a research group at the University of Cambridge, which focuses on what does an industrial strategy look like with absolutely no emissions, so no negative, no offsetting, not just a little bit of emissions left over, completely zero emissions. And when you think of industrial strategy, obviously concrete and cement's a big part of that. And as you said in your introduction, thinking of a world without Portland cement is really challenging. So when our principal investigator on this project posed that question to our group and said, what would a world look like without Portland cement? We couldn't imagine it. We couldn't imagine living in a world that doesn't have Portland cement. And there's different challenges to thinking about that world. So the first one that we look at is the recycling. And as Mark's mentioned, and there's been lots of commentary so far today, the construction sector is actually quite good at recycling and has been for a long time. And we don't really have waste. It's just a different feedstock that we're moving around. But the challenge of having zero emissions is we can't recycle to a lower feedstock. We can't downcycle, because if we downcycle, then we have to keep producing virgin material, and that generates emissions. So when we need to think about recycling with absolutely no emissions, it has to be upcycling. So we need to go from clean aggregate to concrete back to clean aggregate, or Portland cement to concrete back to Portland cement. And that's would enable zero emissions production. So that's one side. How do we do that? That's one question, one problem we've been trying to solve. the next problem we've been trying to solve, and I don't have to tell you this graph because you've heard it loads of times already this morning, is where the emissions come from. And cement's double trouble. You get emissions from the chemistry and the process that's happening. You also get it from the fact that you need heat. And to produce high temperatures, it usually has emissions and fossil fuels involved. So we were looking at both sides of those. How do we convert production so you don't have any emissions at all, both for heat and the chemistry? And then how do you create a process that you can repeat again and again and again, and you're not losing the value of the materials that you're using? And the invention that Cyril Dunant, who's one of the researchers in our group, came up to in response for this, we've called Cambridge electric cement. And it's electric cement because it's produced in an electric kiln. And the process that we work through is we take demolition waste and process that to separate out all of the components. And what we're left with, and the bit that we want from it, is what we call the recovered cement paste. But the byproduct from our process is a really clean aggregate that should be as good quality as new aggregate. So there's extra benefits in that. We take the cement paste out. I'm going to explain it. My description is not going to be that great. There's a really nice video on YouTube that you can watch it with some graphics. So it's too long, but feel free to watch it. It hopefully will make sense. So we take the recovered cement paste, and that eliminates our process emissions because the material has already released the carbon dioxide the first time it was produced. And as long as it hasn't had too much recarbonation in service, it shouldn't release more carbon dioxide when you re-clinker that to use it again. So the next challenge is how do we re-clinker, how do we provide that heat? So we looked at an electric way of providing that heat so that you can then decarbonise the electricity grid, which enables you to produce it without emissions. And we already have a high temperature electric process in our sector already, and that's steel recycling electric arc furnace. So we're using the electric arc furnace as a heat source. So we're using the molten metal and electric arc furnace to heat up this recovered cement paste. That reclinkers it, and then if we cool it rapidly enough, we get the right phase composition for the equivalent of OPC, and that's what we're aiming to do. That's actually quite beneficial for the steel sector because they currently use lime flux as a slag in their process, and if we're replacing the lime with recovered cement paste, then hopefully that can reduce some of their emissions as well associated with their lime use. So that's the process of Cambridge electric cement, and as I say, have a look on the video, there's a bit more detail there. But how do we go from a university lab, an idea, we've made a small amount of it, to actually doing that in real life and completely generating a whole new supply chain that has connections, material flows in different ways and is used differently. And that's where Cement to Zero comes in. So it's an Innovate UK project, and when we started the project, we'd made about 10 grams of this cement, and then hopefully at the end we'll have made 20 tonnes. And that's the kind of transition, which I know is small for you, but for us at the university, 20 tonnes is really big. So here's a short video that takes you through where we're up to so far.
Cement to Zero is a £6.5 million Innovate UK grant-funded project. It's led by the Materials Processing Institute, supported by University of Cambridge, Alpha Beatty, Atkins, Tarmac, Celsa and Day Aggregates. It provides an excellent opportunity to showcase a net zero cement, which will be incredibly positive for the UK.
Yeah, so at the university we're looking at the fundamental science behind this Cambridge electric cement process, and we're trying to work out how you can make zero emission cement in an electric arc furnace.
Today is part of the important steps of the project to understand where the science meets the practical aspects of creating a slag that ultimately can be upscaled to a large electric arc furnace operation. So we're principally interested in knowing that the chemistry of the slag is correct, but also the physical properties, the physical characteristics and the behaviour of the slag inside an electric arc furnace. It's very important to make sure that all of the criteria is satisfied and that we've completely de-risked the slag technology and the way that it performs in this small arc furnace, in this test environment, before we can move up to a large-scale operation.
With the Cement to Zero project, it's really helpful that we can test what we're doing in the lab and a small-scale environment in a much bigger pilot-scale environment. So if we're successful today, this will be the first time that we've made cement in an electric arc furnace, which is really exciting for us.
The key statement there was if we are successful today, and we weren't actually successful on that day, but if we are successful soon, hopefully we'll get there. So the trials at the moment are really promising. We've managed to prove out that making cement clinker in an electric arc furnace doesn't damage the furnace and doesn't negatively affect steel production. So that's really important for us to be able to move to the next step, which is from these pilot scale melts into the full scale trials, where we'll do that at the full scale electric arc furnace in Celsa's site in Cardiff. And then once we've produced, hopefully, enough of the slag, which is cooled and ground to be clinker and processed, then we're working with Tarmac and Balfour Beatties and Atkins to try and use that in an on-site application. And it was interesting hearing some of the talks this morning about the challenges of needing to do it in temporary works and how we want to test it as much as possible in a real scenario, but obviously de-risking the process as well. So the aims of the Cement to Zero project, it's the first time we will have made anything at scale. So we're not going to understand everything. This is just starting to explore what this technology could look like and how a new system and a new supply chain could be built around this technology. So what we're aiming to understand is a bit more about the technical feasibility and to also understand the commercial feasibility. So do we have all the steps in the supply chain in the UK already? Do we have the technology to implement this? Or is there new innovation that's required to enable it to succeed? Then at the end of this project, so this project's going to run until September next year, so we've got just under a year left, then we need to start the extensive programme of validating the material and trying to think about how you would scale up production. So we're going to make one batch of 20 tonnes, and then we think if you're going to do that regularly, how would you do it differently to do it at scale? So we're really excited about this. Obviously, you can't buy it yet. It's not available to use yet, and we've got quite a bit of time that we'll have to wait until we can actually make the most of some of these new innovations. But I'd like to think that we don't just need to sit around and wait for this new kind of technology to come through. There's lots that we can be doing so that when it is ready and when it is available, that we can use it most effectively. The first one is around material efficiency. So whether it's our process, whether it's kind of some of the other technologies that have been discussed, our assumption is that zero emission or really low emission cement isn't going to be available in really high quantities, really cheaply. Hopefully it will be, it's unlikely. So we can think ahead and see how can we value that material more. So how can we deliver the same level of service but with less clinker, because that's where the emissions are. So thinking of opportunities for eliminating waste, prioritising material consumption. So at the moment it might be that in order to reduce labour costs you increase your material consumption. Perhaps that dynamic will change if the cost of the materials is increasing. And then thinking of the value of waste. So if we have demolition waste and it's crushed and it's mixed, how do we do additional processing in order to increase the value of that product so that we can then, instead of having a waste, we have a feedstock? And at what point is that economically viable? They're all questions that we can start to think about now. The next one is on the innovation side. So the desirability, I don't know if you're familiar with this, is the kind of the three circles of innovation. So for innovation to succeed, you need to want it, it needs to be possible, and it also has to be able to make you money. And at the moment for our Cambridge Electric Cement product, we think there's a demand for it, but actually some of the metrics don't always line up when you look at Scope 2 and Scope 3 emissions. At the moment, there isn't a huge amount of incentive for steel makers to let us use their electric arc furnaces to make cement. So the system might desire it, but does each individual person in the supply chain benefit, and are the motivations in place for it? Feasibility, we're working on the technical feasibility. There's a long journey to go on that, and I think it would be brilliant as we look forward to increase collaboration, do as many tests as possible, and to validate these materials. The same with some of the other innovations that are coming through. We have much closer collaboration between the university and industry trials, so that we can scale it up quicker. And then the final one is looking at the business model. So all of our research at the university is based on demand reduction, so using less material as a way to reduce emissions. But obviously we don't want that to also equal making less money and economic slowdown. So we need to think creatively about how we can disconnect the amount of materials that are being used with the service and the benefit that society is having, and the value that we put on that service. High growth recycling opportunities we've touched on already. I'll pass it back to you, Mark, I think.
So I'm aware of time, so I'll probably skip over some of the last slides. But really, I think what Philippa's shown and what the work around the Cement to Zero project has really shown is it's a mixture of things. So where could it go? It's about good design. It's about valuing resources. It's about understanding what assets we've got at the moment. We could be sitting on a huge feedstock of materials that could be potentially used or reused again. The Industrial Energy Association has now got it on their roadmap as well. I think they're saying they're predicting a 93% share of near zero clinker production through what they call deep reductions, requiring a massive rollout of innovative technologies such as cements made with alternative raw materials and carbon capture and storage. So it's part of the mix. A question that I had, and I still have in the project, is will there be enough material, for the industry? The team at Cambridge have looked at this. They are very rough numbers at the moment, but they're thinking that there's potentially enough material or stock to make about 25% of the cement demand in the UK at the moment. Limiting factors, as Pippa mentioned, steel production and furnace availability and so on. It could go up maybe higher than that. If we're looking at material efficiencies, we could potentially save more. So yeah, a real mixture of things that we need to think about. Just want to touch on project successes so far. So they're across kind of three main areas. Pippa said we're halfway through. We had our Q4 meeting a couple of weeks ago. The first one is really, and I think we all agreed on this, is the teamwork and collaboration that we've all kind of experienced. Some of the project partners have worked before as companies, but as individuals, we're kind of all getting to know each other, and the collaboration so far has been a real success, probably the main success so far. And that's what, and PAS 2080 as the carbon management guidance has been mentioned quite a few times this morning already, and one of the aspects of that is value chain collaboration, and this is value chain collaboration in action. The second success, I would say, is that the Innovate UK structure really keeps you focused, it keeps you on task, it makes you report on time. It just helps when you're treating it like a project to deliver for a client. And then lastly, commercialisation discussions I think have really been successful as well, and we're probably not even halfway through them at the moment in terms of what we need to think about in terms of thinking about the system and how cement or the project the product can be manufactured. But yeah, good so far, halfway through it. And then lastly, just to bring Doc Brown back in again from the future, I'm just going to finish on 3 points. As a designer, my background's in highways design, I'm not a structures engineer, I don't know a huge amount about concrete, but the main points that I think we want to get across is design is important, and when we talk about design, quite often we think about designers need to do everything, which, fair enough, probably the majority of it, but everyone involved in that value chain has got a responsibility to think about the design holistically, and the impacts that their decisions can have on the design process. Internally, not me, but one of my colleagues had some engineers in his team run through, I think it was a flood wall on piled foundation design, and they looked at, and this was constructed, and they looked at the design again and what they could have done if they had a bit more time, less outside influences, certain assumptions, etc. And they were estimating that in certain instances they could save quite a lot of carbon emissions, up to 50% in some instances, on certain aspects. So all of these influences have an impact. So we need to bear those in mind. Second point is really the experience of the rack concrete recently. We are aware as a team of the risks as well as the opportunities involved in something like this. So, you know, that is something that needs to be managed quite closely. And just to finish, case studies. So again, if we were to look at the case study that I talked about earlier, on that project, it produced 400,000 tonnes of, well, not the project, but the reused material was 400,000 tonnes of concrete demolition waste. Throwing some rough numbers at it in terms of what the project is looking at the moment, that would produce about 40,000 tonnes of cement, and that could create about 120,000 cubic metres of concrete. And using Rachel's example earlier of the Central Reserve concrete barrier, I think my calculations are right. I've not had them checked, but I think that's about 170 kilometres of concrete barrier. So, and I did a quick calculation earlier when David was talking about the CRCP, and I think per linear metre on a motorway, I think that's about 40 kilometres of that as well. So, huge potential, and quite an exciting project. So,
I forgot to.
sorry.
Yeah, I should have mentioned we've got a little goodie bag of some of the experiments that my colleague Patricia was doing earlier in the week in Teesside, where we've got the first trial. So this is you're welcome to come have a look at it when you have a coffee later. That's some of the slag. It doesn't feel like clinker, but it will be ground, processed, metallic separation to take out some of the steel that's mixed into it, and then what should be left should be a clinker that's the equivalent of Portland clinker. So come have a look at those if you want to start. Thanks.
Thank you, Paul and Philippa. Any questions, please, on Cement to Zero? Paul, what we?
Right, so it was not really a question on the cement, it was on the aggregate, because you said that you'd come up with a way of getting really clean aggregate, which is a particular issue with crushed or recycled concrete because of the water demand. So what was the best way of doing that, and what scale can you do that on?
Good question. The best way is still being developed, so there's lots of different pathways, and at the moment we're finding a trade-off between how much cost and energy you put into that separation versus the value add that you have from that. The research that we're doing, and on that stage it is still research at the university, we haven't scaled it up yet, is looking at a combination of heating. If you heat up the aggregate and then hold it at a high temperature for about an hour and then allow it to cool, then the kind of milling process gives better separation. There's also other innovations there's quite a lot going on in that space outside of our project that we're watching to see. Hopefully someone else will come up with a better way of doing the separation. And the trade-off we have is if you have perfect separation, in theory we can replace the lime completely in an arc furnace with the RCP. If you don't have particularly good separation, then you have to put more lime in there, but you can still produce. So it's a kind of the scale of, are you at zero emissions or do you have an 80% reduction in emissions? And then depending on the quality of that separation process, you get it somewhere in between. Okay.
Any further questions? Good for you, Philippa, because you could dash off.
Yeah.
Many thanks
Thank
to
you.
you, Philippa, and to Paul.
Mark.
On Mark, for showing us where the future lies with CO2-free concrete. Thank you.
Thank you.